Hello, and welcome to today's podcast from the ALLATRA Global Research Center. My name is John An, and I'm your host. So micro nanoplastics are being detected in more and more places, in the air we breathe, the water we drink, and the food we eat. And yet scientists still face one of the most fundamental challenges in this field. That is, how do we accurately detect and measure particles that are often too small to see? Today, we're joined by Dr. Balaji Rao, Assistant Professor of Civil, Environmental, and Construction Engineering at the Texas Tech University. Dr. Rao specializes in contaminant fate and transport. It's essentially understanding where pollutants come from, how they move through our environment, and where they ultimately end up. His research focuses on identifying and characterizing micronanoplastics in complex environment samples, including stormwater, sediments, and biosolids. And he's helping us address one of the most critical questions the researchers face. How can we ensure that the measurements we make are trustworthy? Today, we'll explore the challenges of measuring micronanoplastics, the pathway these particles take through our environment, and new technologies that may help us understand better their potential risks. So, Dr. Rao, welcome, and thank you so much for being here with us today.
Thank you, John. It's a pleasure to be here.
So before we dive into micronanoplastics, I want to start with your own journey. So I want to know, how did you find your way into the environmental engineering, and what sparked your interest in understanding what happens to pollutants once they enter our environment?
Yeah, it's a great question, and I would say that it was not an intentional pathway for me to explore environmental engineering and in fact do a PhD in environmental engineering. I grew up in southern part of India in a big city called Chennai, and I did my bachelor's in chemical engineering and worked in a oil refinery, a petrochemical refinery, in fact, which is now one of the largest, or probably even the largest petrochemical refinery in the world. And so I never had an intention to do environmental engineering. My first exposure to plastics was in the petrochemical engineering company, where there was a polypropylene unit that was making polypropylene pellets. But I never envisioned, I would end up in environmental engineering. I did work in the refinery for about 3 years, and then I decided to do my higher education. I came to West Texas at Texas Tech University. I did my master's in civil engineering, followed by a PhD in civil with focus on environmental engineering. At that time, my research area was focused on characterizing a thyroid hormone disruptor called perchlorate, which was used in rocket fuels as ammonium perchlorate. And the research was about whether the perchlorate that we find in the environment is primarily due to these manufactured uses, or is there an alternative source? And it turns out that there was a natural source of perchlorate that is likely formed in our atmosphere and deposited in the terrestrial environment. So it was a very interesting direction that the research took, which was not what we expected. And following my PhD, I did a postdoc in Oak Ridge National Lab. There is a bit of history in Oak Ridge National Lab. It is the place where the uranium was extracted for the first atomic bombs. One of the processing that they were using was mercury to separate these isotopes. And mercury is a neurotoxin. And if it's not disposed properly, it will end up in the environment. And that's what we saw in that location. And I switched gears from perchlorate into looking at a more classic contaminant, mercury, and how it moves through the environment. And I don't know if you've been to that part of Tennessee, but it's a very ecologically sensitive place with a lot of streams and lakes. And so mercury tends to kind of stick to the environment, move across these biological compartments, move up in the biological trophic levels, bioaccumulates in the environment. Kind of a segue to what happens when microplastic is released to the environment, likely. And so what I was working on, how mercury moves to the environment, how can we better detect some of the transformation process this mercury undergoes that involve development of novel analytical techniques to characterize this. Eventually, I got an opportunity to move back to Texas Tech, focused not only on addressing the problem of contaminants, transport, and fate in the environment, but also how do we mitigate it? And that's what got me really excited to come back to Texas Tech. This is not a typical path that the researcher takes. You don't generally come back to your alma mater, but that was an opportunity that I couldn't miss. And I was focused on how do we mitigate contamination, particularly in water systems and in sediments. And one of the projects that we were working on, and I can talk about that in more detail, was stormwater from urban industrial environments, how they can carry pollutants in the particulate matter in the stormwater and how they could end up in the sediments. And that was my initial introduction to characterizing microplastics. The original focus was on characterizing contaminants such as mercury, polycyclic aromatic hydrocarbons, which are typically found in these stormwater matrices. But at that point, there were some interest in characterizing what we call as emerging contaminants that included microplastics and PFAS, which is also called as forever chemicals, in stormwater samples. And we started exploring and adapting our analytical techniques to characterize these emerging contaminants. And that was my introduction to microplastics.
Microplastics, they're everywhere, and they were not very popular for some time, maybe until about 5 years ago. I mean, it used to be, people wrote about it, there were articles, but it was very few. Now, like every day there's this new article about micro nanoplastics. So I mean, you touched on this briefly, but like, what really attracted your attention to these particles? I mean, what convinced you that developing developing way to detect these particles, especially in like storm wars and whatnot in these complex matrices, it's very complicated. And so what drew you into this topic of micro nanoplastics, and what convinced you that we need a reliable way to measure them, and this is one of the important challenges that we need to tackle? Like, what was that enlightening moment?
Yeah, so going back to that project on stormwater, one of the hypotheses that we wanted to test is until we started working on this project, many of the techniques for characterizing stormwater focused on either bulk characterization of the water without paying much attention to the particles that could be present in the water. And why does it matter? And when I'm talking about particles, I'm not necessarily referring to microplastics, even though they may be present in the stormwater, and they are. I'm talking about these sediment-laden particles that are kind of eroded from the environment as the water moves through these channels and through these streams. And these particles have an affinity to basically grab contaminants as they move along with the water channel. Our hypothesis was it's not enough to do a bulk characterization of the water, because what you're missing out this information in terms of what these particle-laden pollutant would behave. Particularly, how does the size distribution of these particles affect their fate and transport? And perhaps from an engineering perspective, what does the size distribution of these contaminants in these particles mean in terms of how they could be effectively removed from current stormwater treatment systems? What some of these treatment systems could be as simple as like a retention pond that just lets the particles settle down, or they could be more advanced where you could have cartridge-based filters to specifically remove contaminants that are present in the stormwater. And so the hypothesis was the particle size distribution has an influence not only on how contaminants behave in the stormwater, but how effectively they are removed as well. Now, that has a strong correlation with microplastic research as well. So microplastics do not come in one specific size. They come in a distribution of size, potentially a continuum distribution. And that could affect how they move in the environment, as well as how they are removed by current technologies that may not be specifically designed for microplastic removal, but they may still be removing some of these microplastic material. Long story short, what we did find is the coarser particles that are typically greater than 20 microns, irrespective of whether it's microplastics or background sediment material, they tend to be effectively removed by these stormwater control measures, which is the good news. The not so good news is those smaller microplastics and potentially nanoplastics and these nanoparticles are likely not removed by these treatment systems. So we need to start thinking about developing better engineered systems to remove these particle sizes.
Yeah, great. So yeah, we're talking about these particle sizes, and maybe sometimes confusing to a lot of people. People talk about microplastics, nanoplastics. So before we go deeper into micro nanoplastics, let's start with the basics. So these terms, micro nanoplastics, they're discussed together, and again, they're not exactly the same thing, right? So for our listeners, who may not understand this difference, why? So first, what is the difference between the two, between micro and nanoplastics? And second, why is detecting the smaller, the nanoplastics more difficult than its counterpart, the microplastics?
So yes, the general definition of microplastics has basically an upper limit and a lower limit. The upper limit is well defined. It's defined as any plastic particle that is at or less than 5 millimeter in size. Now, where nanoplastics begin technically is any particle that is less than 1 micron or 1,000 nanometer would fall under nanoplastics. So that size is important. That determines what we can see. And microplastics, the larger microplastics, this is like something around millimeter size to these larger micron sizes. For instance, our human hair is about 100 micron. We can certainly see those particles. But once we start looking into these smaller microplastics, anything less than, say, 10 or 20 micron, all the way to nanoplastic, it becomes increasingly difficult see using visual microscopic techniques, and also to confirm whether these are microplastics. Then you need not only just visually identify these as microplastics, you also need to have a way in which you can actually say that, hey, this does look like a microplastic and not the background sediment material, just like the example that I used in stormwater, where much of the particles that you would find in stormwater or in other environments are likely not going to be micro nanoplastics. It's literally like looking for a needle in a haystack. So these particle sizes are very difficult not only to see, but also to confirm that these are microplastics. And that requires a technique that typically combines some sort of a microscope with that of a spectroscopy-based technique, which can characterize down to the smaller microplastic sizes. But then all bets are off when you want to probe down to the nanoplastic sizes. Some agencies tend to indicate that the lower size for micro nanoplastics is all the way down to 1 nanometer, which currently we do not have techniques that can characterize environmental nanoplastics down to that really small nanometer sizes.
So here we go. Just general consensus is that the smaller the particle gets, the more harmful effects it has, just because it has, for example, more surface area compared to volume. And it's not just identifying these particles, but you're also the measurement is also complicated by the fact that you're identifying these in a very complex matrices, like biosolids and in human bodies. So could you also walk through like what the procedures like, what the limit again, what the limitations are? Can you give us more details how these are measured and what the challenges are?
That's a great question. So I would say that the challenges depend on what matrix you're looking at. Drinking water is a relatively clean matrix. And so typically you don't have to do a lot of processing of the sample before you characterize it. So I would compartmentalize detection techniques into three different stages. One is the sample processing stage that includes sample collection and how we process the sample. How do we load these samples that potentially contains these microplastics onto a platform? Typically, we would use a filter to load these microplastics or to separate it from the water and other constituents that are present in the environmental sample. And then you have the analytical technique that actually detects and identifies these micro nanoplastics. And then you have a post-processing techniques where you get these signals and these spectra, as you will, from these analytical techniques, and then you match it with an existing library of some sort. And then you say that, oh, this looks like a polypropylene, or this looks like a polyethylene, and so on. So all these different stages comes with its own challenges. When it comes to a simple matrix, I call it a simple matrix from an analytical perspective, like drinking water, the initial sample collection processing stage, the only thing you have to be mindful of, the sample does not come into contact with any plastic material. You use non-plastic material to collect the samples, and you use apparatus such as vacuum filtration apparatus to load the samples onto a filter that does not have plastic materials. So more often than not, that's the main concern with that. But when we talk about more complicated samples in the other part of the spectrum in environmental samples like biosolids or sediments, you also have to deal with really large amount of other constituents that are present in the sample, like organic matter, sediment particles, inorganic particles that from just visually may even look like potentially some microplastics, or microplastics could be embedded in them, so you can't really see them. So it's not only enough to properly collect these samples, but these samples may have to undergo some sort of what we call as digestion techniques to remove these background material that are not plastic, and then potentially apply some sort of a physical separation techniques like density separation to concentrate these microplastics that are present in these samples. And then you go to the stage 2, where you start applying the analytical technique, which is common for all these different matrices. And then you also have to then deal with the post-processing, where you have to compare it with libraries and so on. So during this entire process, what you come across is, as the sample complexity increases, you need to really adapt your techniques to minimize interferences, minimize contamination, while also making sure that the analytical techniques and the post-processing techniques can be validated across different labs. That is part of the current issue with analytical characterization of microplastic. Is if I take the sample that I collect in Lubbock, if I send it to Washington, to another lab, and ask them to characterize microplastics, and I characterize the same sample in my lab, it's likely that we come with completely different results, depending on the techniques that we use, depending on the processing methods we use, the digestion techniques we use, the analytical techniques we use, and the post-processing applications that we use for these samples.
Is that
So
why different groups get different results? I mean, you have sometimes like, oh, it's the same sample, but are they getting different results because of they have different digestion procedure or they're using different techniques? Is that why some of the groups are getting different results, even though they're sort of looking at the same samples?
absolutely, and that is part of the problem which the analytical community is trying to address. And they are starting with something that's relatively easy to deal with, the low-hanging fruit, yet more important exposure route, which is the drinking water. So the drinking water is relatively less complex, and there's been a recent interlab study, it's published out there, where they show that the size matters when it comes to confidence across these multiple labs in coming up with the same results, in other words. So particle sizes that are microplastics, particle sizes that are less than, say, 20 or 50 micron, all bets are off when it comes to characterizing these plastics and validating the results across labs. But those larger microplastics, there seems to be a lot more confidence across the lab that as long as we follow these specific protocols, we should end up with the same microplastic distribution and those results like, X amount of polypropylene and Y amount of polyethylene, they seem to match across the labs. But when the particle sizes are lower in the smaller microplastics, certainly nanoplastics, then all bets are off. You may get completely different results among the labs. There is too much variability among the labs to say that, okay, this is what we would see in the sample.
And so for those small particles, I mentioned earlier that in just a general consensus should be it seems to be that as the particle gets smaller and smaller, it gets more toxic, but it's even harder to detect. So what is needed? Do we just need a standards method that really works, that's proven? Or do we just need a better instruments? A better instrument needs to develop. What is needed to detect those very small nanoparticles, which are very toxic to humans and their living organisms?
We do need a lot more of these kind of interlab studies because there were some interesting conclusions from these interlab studies and recommendations on how we can improve in characterizing these really smaller microplastics and nanoplastics. And what we need is more research efforts, starting with more funding, on how we can, work together and develop more standardized and validatable methods, particularly for these smaller microplastics and nanoplastics. And that starts with, the scientific community kind of working together across different research groups, not working in silos, that you would often see papers that even in drinking water, everyone seems to use different methods. And so, it's very hard to compare results from these different research papers. So what we need to do is sit together and come up with methodologies that we try and standardize, and that way we can validate, these methods what they can do and what they cannot do. Now, I do need to say that when it comes to nanoplastics, some of these methods, no matter how much we sit together and work on it, is not going to work. Like a traditional micro IR spectroscopy techniques have limitations in terms of what spatial resolution that they can characterize. I would say anything less than 10 microns, no matter how much effort you put into it, you may not see validatable results across the lab if you use this technique. There are other techniques like Raman spectroscopy that have been proven to characterize down to 1 micron. So there is a little bit of an improvement when we apply these Raman spectroscopy techniques. But then nanoplastics is something that is really, really new at this point. And there is no agreement on what are the analytical techniques to use for nanoplastic characterization. And so standardization is still a long way off when it comes to nanoplastics. So I would
Great.
say the low-hanging fruit for standardization of methods is likely in the next 5 years or so, is likely going to be at the microplastic scale, potentially down to 1 micron. If we can all agree upon this is the method, this is the approach, and this is how we need to process the sample and analyze the sample and characterize the data that is obtained from the analytical instrument, that would be a big achievement. But if we want to talk about nanoplastics, I think we are still a way off from that.
Great. Yeah, thanks for sharing your insights on the measurements. Now, I want to move on to from the measurements to how micro nanoplastics, where they come from, where they go, and well, it ends up in human body. So, like, I want to talk about now the pathway of micro nanoplastics. You know, when most people talk about plastics, they think about bottles and bags just floating in the ocean, right? But many of the largest sources of micro nanoplastics, they come from like everyday activities that people rarely talk about. And what are in your opinion, like what are some of the most important sources of micro nanoplastics that people might not realize they're really contributing to this problem?
You're right. So the major sources are, obviously there are plastic materials that we come across on a daily. Whenever we go to, drive around the road, you see these plastic bags kind of flying across. And so one wonders what happens to these plastic materials, because these are designed to be durable. So they are a big contribution of microplastics into the environment. And these are some of the common sources, like our daily plastic materials, plastic containers, plastic bags, textile materials. These are what we call as, the major potential sources of microplastics into the environment, or derived microplastics into the environment. Some of the less obvious sources, I would say, is one of them that people might not think about is paper cups. So you would think that what does paper cups has to do with plastic sources? It actually turns out that for paper cups to hold liquid, they need to have some sort of a plastic lining inside those paper cups. Otherwise, they will not hold liquid. And so those plastic linings could be made of, polyethylene type of, and they could leach microplastics, particularly if you put hot liquids such as coffee into these paper cups. And they could be leaching plastic materials into those liquid, and you could be drinking directly those microplastics as you have this coffee in these paper cups. So these are less obvious sources. Other less obvious sources are paints. We often don't think about microplastics when we talk about paints, but paints have a significant amount of microplastics in them. In fact, there's been a recent article that talks about how paints have been understudied as microplastic source, even though they have, percentage levels of microplastics that is kind of, they're manufactured to have microplastics, particularly water-soluble paints are manufactured to do that. And so it's not inconceivable that during the application and during the normal aging process of this painting, wear and tear, that there would be release of microplastics into the environment, which has not been properly accounted for. And I would say when we talk about sources of microplastics, we start with something obvious, that plastics that we can see with our naked eye. So that obviously becomes we tend to lean towards those as major sources. But there are these hidden sources of microplastics, such as these paper cups and paints, which we need to evaluate more on how these sources contribute. Eventually, when we talk about the impacts of microplastics, we are talking about how it affects our health. So I think what I was talking about is the less obvious sources of microplastics could be a pretty significant source, exposure route, rather, when we talk about consumption. So a plastic bag in the environment may have potentially contributing a lot of microplastics in the vicinity of where the plastic bag is, but we may not be in direct contact with those microplastics. But whereas a paper cup, which may not have a lot of microplastics in it, but you're directly coming into contact with that. In other words, it's not just about what is the total source of these microplastics in the environment, how we come into contact with these different microplastic sources is equally, if not more important, when we talk about the impacts of these microplastics.
Yeah, so you're alluding to, okay, there's a source of microplastics, and of course, they don't just stay in one place. They move around, they go, everywhere. For our listeners, like, could you walk us through how these micro move around the air, soils, water, and wastewater systems, like including stormwater, biosolids along the way, and how do they eventually end up to humans? For the humans, like, what are the very well established methods? I know, like, we're breathing, we're eating all these microplastics, and which ones are not really well established or which ones are not well known. So just walk us through that journey. So, like, the plastic is released, how do they travel through the environment, and how do they end up with us? Just paint that picture for us.
So yeah, great questions, and let me try to break it down into multiple, thought process on how this would evolve. The fate and transport of contaminants in the environment, whenever we talk about this, is not just from plastics, but contaminants in general, both physical and chemical characteristics of these, in this case, microplastic particles, would matter. What do we mean by the physical attributes? The key physical attributes that we care about, we talked a lot about this, is the size. It is logical to infer that the smaller the size, the more widely they will distribute into the environment. Now, that could also mean that they would get diluted into the environment, but that it just gives you the extent in which they would impact the environment around you. The larger the sizes, they may not move through the environment as much as the smaller micro and nanoplastics. Then you talk about the density of those microplastic particles. The more dense they are, when we talk about sediment or aquatic environments, the chances are they would end up in the sediment, and then you may not be directly exposed to it, but those benthic organisms and the fishes that feed into those ecological environment, they may start accumulating the micro nanoplastics. And if we eat those, fish, then we would get indirectly exposed to the micro nanoplastics. The less dense microplastics may end up directly into your drinking water sources because they are basically floating in the water and they are easily moving across the water compartments and eventually end up in drinking water sources. And some of these have known to be passed through the drinking water treatment systems, and they end up in your as you open the drinking water tap, they may end up in your drinking water as you consume that drinking water. So that matters as well. Then the chemical attributes matters too. In terms of chemical attributes, we talk about hydrophobicity of these plastics. And what we mean by that is hydrophobicity is another term of indicating whether how much it likes to stay in water as opposed to stay away from water in very layman terms. The hydrophobicity determines whether these plastics are sticky. They tend to stick with particles as they move through the environment, or they are less sticky and they tend to stay in the water. And as I mentioned earlier, they cause different sort of transport through the environment and lead up to different kinds of exposure in the environment. Recently, there is a lot of focus on the aging of these microplastics. One of the things that these microplastics, as they age in the environment, they undergo some physiochemical changes. Particularly, they start having incorporating more potentially oxygen groups into their superficial material, and they could change the charge of these microplastics, and that could change the behavior to the environment as they transport through these different environmental compartments. And so all these attributes of micro nanoplastics matter. And interestingly, the techniques that we discussed earlier are not capable of simultaneously evaluating all these different attributes. Like, spectroscopy-based techniques can give you particle size distribution. It does have limitations when we talk about nanoplastics, but it can give you a particle size distribution along with the polymer chemistry that is associated with the particle size distribution. But it does not give you information on the charge of those particles. To some extent, it would not give you information on how much weathered these particles are. And some of the concerns of micro nanoplastics, which I don't think we got a chance to discuss much about, is the additives and pigments and dyes that are incorporated into these plastic materials, which may cause a larger adverse impact into ecological and human health than the plastic material itself.
Yeah, it seems like it's a very complex problem that you have to measure. I mean, you're challenged by size. You have all kinds of chemicals attached to it. You have all kinds of different charges, different, I'm guessing, heterogeneity within the particles. It's a very complex process, and it seems like we don't have all the tools that's necessary, or at least standardization to measure all this. So, looking ahead, what new analytical tools or what new technologies are you most excited about, or is there anything in the pipeline that you know about? And how could they improve the ability to measure these particles accurately, consistently, and at scale? Like, is there something that or something you're excited about in terms of measuring all these micro nanoplastics and complex matrix systems?
So, in my opinion, a single technique cannot measure all the attributes that we just talked about, and the attributes that are, again, key to microplastic characterization environment is definitely the size, the morphology or the shape, and the potential charge that the microplastic carries, and the additives, the polymer chemistry, of course, and the additives that is associated with this microplastic. So a single technique is, to my knowledge, is even the most cutting edge technique that we have come across are not capable of doing all of this together. So it's likely going to be a combination of techniques to do what we would really like to characterize when we talk about microplastic impacts in the environment. Having said that, much of the research, microplastic research groups have focused on characterizing the size distribution along with the polymer chemistry. And the challenges that we addressed when we talked about characterizing the small microplastics and nanoplastics is something that there are some novel emerging techniques that seem to address it that has got me very excited. Two of them that I would like to mention is based on what we call as the pump and probe technology. That basically it overcomes the size limitation by using, say, for instance, using IR spectroscopy, where you use IR light to hit the particles and to differentiate whether it's microplastic or whether it's a background material. But you still have the spatial limitation. You overcome the spatial limitation by using a probe, which could be a visible light, which has a much smaller wavelength. So in general, the smaller the wavelength, the smaller the particle size you can see. That's why we use X-rays to look at really atomic scales, because X-rays have really small wavelengths. So you can look into these really nano and atomic scales. And so the same principle is applied here, where you adapt these IR and Raman-based techniques, combine it with highly spatially resolved techniques, such as the optical photothermal IR spectroscopy, and something that can really do nanoparticle size is the technique that couples atomic force microscopy with IR spectroscopy to characterize down to the nano size scales. Now, we can indirectly characterize these nanoparticles using thermal-based techniques, which the principle behind that is you take a sample and you increase the temperature in the absence of oxygen, a technique called pyrolysis, and you break down those plastic materials, and then you look at the breakdown products to infer what type of plastic it's made of. This works at even nanoscale, because size does not matter for this technique. It's more about how much mass of plastics you have in your sample. That is the limitation, not the size. But the not so good news is you do not get information on the size distribution. All you can say is you have X amount of polypropylene or polyvinyl chloride and so on. You do not get information on the size distribution. And so that is a catch-22 situation that we are dealing with when it comes to characterizing these different attributes of both the micro and nanoplastics. And at this point, I don't see a single technique doing everything that we want from these characterization activities. It's likely going to be a combination of techniques.
I don't know. I think what we need is a standardized method, and it looks like we do have, or at least we have some idea how to measure even like smaller particles, and like in order to have a standardized process with the right techniques, how do we get there? I mean, how do we move towards having a standardized solution so that whenever we read from papers to paper from different research groups, we have the data that is reliable, that is reproducible? How do we get there?
That is an excellent question. I have thought about this for quite some time now, and I don't think there is a perfect answer to this. And coming back to drinking water, which is where many of these validation studies have focused on, they have found out ways in which they can make standard samples embedded in pellets that they could basically, you put those, it's a mixture of plastic material of known size distribution that is in this pellet that is dissolvable in water. And you can put that pellet into the water, and then you create this sample that contains this mixture of microplastics. And then you send it across lab to validate whether they are getting an accurate distribution of this plastic. Now, that works nice for drinking water, sort of a matrix. But when we talk about more complicated matrix, biosolids, sediments, and when we talk about human biological samples or fish tissue samples, I think that we are not there in terms of what represents a standard material. I don't think there are easy answers to that. One approach that we use in our lab in terms of validating our technique is to intentionally spike known amounts of plastic material into these biosolid samples and look at the recovery. Now, if I spike 100 particles of polyethylene, do I recover that 100 particles of polyethylene as I process these samples into these three different stages, as I mentioned, from the digestion to the analysis and the post-processing? If I'm not able to recover all the 100 particles that I spiked, then along these characterization steps, something is causing me to lose those particles, and I need to revisit where I'm losing those particles. So that's something that is an indirect way in which we try to validate our methods. Now, I know NIST is working into, which would be the National Institute of Standards and Technology. They are working into developing materials that contains known amount of microplastics that mimics these environmental matrices, and using those standard materials, then the labs can validate whether their techniques are capable of characterizing these microplastics. So that's still in the pipeline, to the best of my knowledge. But once these materials are available, I think this will really be helpful to the microplastic research community.
So, in terms of these samples for standard measurements, like I mean, you're talking about like pure, meaning like these virgin plastics that are fragmented to certain size distribution, right? A lot of plastic, I mean, most of the plastic we found is not virgin. I mean, it's covered with all kinds of lipids and proteins and, whatever's in the environment. So would that complicate, in terms of getting, having the right standards or not so?
It absolutely does. And so I think the very first validation is to use the standard plastic materials And if that you don't get good recoveries with that, your method is already failing the very first test. But moving forward, you're absolutely right. We need to find ways in which we can spike environmentally relevant plastic that has undergone these natural weathering process into the sample matrices, and then check if our methods still can characterize these microplastics accurately. And this goes back to my discussion about developing standard materials that already have micro nanoplastics in them with all the lipids and proteins that could interfere with it. I think we are still way off in that. At this point, spiking these plastic materials, whether it's aged or virgin, into these biological matrices is probably the best approach. I can't think of ways in which, like for sediments, we have standard materials that has been validated across labs. And so you have this confidence that this has X amount of mercury in it. And if you were to measure in your lab, you should get pretty much the same results if everything goes well. We are not there yet.
And as a final question, like micro nanoplastic, it's complex to measure and it is everywhere. So it has very complex matrices and maybe feels overwhelming for many people. So as a final message, what would you like our listeners to take away from today's conversation? What would that be if you have one message for our audience?
I would say, let's not panic. So plastics are everywhere. They are ubiquitous. Certainly they seem to have some impacts based on the studies that has been done. But to the extent in which these impacts are causing potentially these issues, human health issues, there is still a lot of uncertainty in that. And much of the uncertainty stems from bulk of our discussion here in this podcast, which is analytical methodology to accurately characterize microplastics, not only in the environment, but also within our bodies. It is still an evolving research. I would take it with a grain of salt. Whenever you come across newspaper reports or research articles that talk about, there is a spoonful of plastics in an average human brain, the chances are there are some plastics in your body, but to what extent you're affected by those plastics and what do they mean in terms of your health issues, there is still a big question mark on that. And so we don't have to panic, but we do need to be mindful of plastic pollution. And I would do the things that you have control over, like, for instance, avoid plastic materials, don't use plastic containers, certainly don't heat plastic containers, avoid paper cups that are lined with plastic materials. So these are the kind of things that you can do right now to minimize your exposure. And as the science and technology evolves in microplastic characterization and mitigation, hopefully we reach a point where we are able to minimize, if not eliminate, the adverse impact of plastic exposure in the environment and in human health.
Yeah, thanks so much, Dr. Rao, for your message, and thanks for being here with us today. And you really helped us understand one of the biggest challenges in micro nanoplastics, and that is how to accurately detect and characterize these tiny plastics as they move through our environment and ultimately reach us. So, thank you very much, Dr. Rao. And
thank you very
for
much,
our listeners,
I appreciate the time taken to have this podcast.
Yeah, and so thanks a lot again. And for our listeners, thank you for joining us. And if you'd like to explore today's topic more in depth, you'll find the links to Dr. Rao's work, along with ALLATRA Global Research Center's review, the report called A Nanoplastics, a Systemic Risk Analysis for Human Health, Ecosystems, and the Environment. And they'll be in the description below. So thank you for listening, and until next time.